Hi, welcome to Math of Chemistry. My name is Dr. English. Today we're going to be talking about empirical formulas. Specifically, we're going to look at what is an empirical formula, molecular versus empirical formula, determining empirical formulas, which is above and beyond the Regents Chemistry curriculum in New York State, but good for that future AP chemistry student out there, and finally some worked examples. What is an empirical formula? An empirical formula is a chemical formula that gives the simplest whole number ratio of the atoms of the element. The focus is on the ratio of the atoms. So let's look at some examples. Our first one is hydrogen peroxide. Hydrogen peroxide has a molecular formula of H2O2. The empirical formula of hydrogen peroxide is HO, where there's an assumed 1 here and here. So what's the difference between these two? The molecular formula is the actual formula that if we had those atoms and we bonded them together with, of course, covalent bonds, we could make the actual molecule of hydrogen peroxide. The empirical formula is the most reduced form, just looking at the ratio of hydrogens to oxygens. So if I divided both of these 2's by 2, I would get a 1-to-1 ratio of hydrogen to oxygen. Now let's look at water. Water's molecular formula is H2O that we see right here. The empirical formula for water is also H2O, since the ratio of hydrogens to oxygens is 2-to-1. For every 2 hydrogens, I need 1 oxygen. So in this case, the molecular formula and the empirical formula are exactly the same. And sometimes that happens. Determining empirical formulas. Fact. The ratio of the atoms in a chemical formula is the ratio of moles of atoms in a mole of the compound. In other words, those subscripts, whether they are obvious, like a 2 or a 3, or assumed, like a 1, indicate the number of moles of atoms in a compound. And you will see questions like this, and it will say, here's a compound, tell me how many moles of a specific element are within that compound. We'll look at some examples of those later. Determining an empirical formula is calculated by converting the mass of each element to moles. That's always step 1. Convert to moles. Then, dividing each mole value by the smallest calculated value, which can sound sort of confusing, which is why we're going to do a lot of examples of this. Finally, the resultant values can be rounded to the nearest whole number if reasonable. Most of the time, you're going to see very reasonable numbers that can just be assumed to be the subscripts in your compound. But sometimes we can't assume that, and we'll look at one challenge problem in this video today. Empirical formula worked example. A compound was analyzed and found to contain 13.5 grams of calcium, 10.8 grams of oxygen, 0.675 grams of hydrogen. What's the empirical formula? Step 1, convert to moles. So we have our masses of calcium, oxygen, and hydrogen. The first thing that we want to do is convert to moles. So here we have the atomic mass of calcium, and we're converting it into 1 mole of calcium. Notice that we can cancel down and to the right, so our units are removed. We are left with moles of calcium. And I'm going to take this out a bunch of decimal places. I'm not going to really think about, oh, it's got to be the 3 significant figures. I'm going to take it a little bit farther than that. So in this case, I have 0.3375 moles of calcium. For the next one, oxygen, I have 10.8 grams of oxygen. The atomic mass of oxygen is 16 grams. Those units cancel. I'm left with moles of oxygen and the resultant value of 0.675 moles of oxygen. Finally, going from grams of hydrogens to moles of hydrogen is also 0.675 moles of hydrogen. So step 1 is just converting to moles, making sure that you have your setup, making sure that your units cancel. Do not shortcut steps on this. Empirical formula worked example, step 2. Divide each by the lowest number of moles. So we could see from our previous work that the lowest number of moles calculated was 0.3375 moles of calcium. Now what I'm going to do is I'm going to divide each of my other values by that lowest number. So of course, 0.3375 divided by itself will be 1. 0.675 moles of oxygen divided by that lowest value will be 2. And the same will go for hydrogen. These now are my subscripts in my formula. So step 3, round to the nearest whole number if needed. In this case, we're sort of lucky. We don't have to do that. And finally, step 4, place them as subscripts after each element. So if I took this literally from what I calculated, I would have Ca with a 1, which we know ultimately would not be included, O with a 2, and H with a 2. And technically that would be correct because I'm taking those values and I'm just plugging them in as subscripts by those elements. More commonly, though, if we took what we wrote at the bottom, we would see this as CaOH2. Let's look at another example. A 1.5 gram sample of a compound containing only carbon and hydrogen, also known as a hydrocarbon, is found to contain 1.198 grams of carbon. Determine the empirical formula for this compound. So we have a total sample of 1.500 grams. That's our total sample amount. We know that 1.198 grams of that is going to be carbon, which means the other mass amount must be hydrogen. So if we subtract these two, we get 0.302 grams of hydrogen. Now we have the masses for both carbon and hydrogen, so we're going to convert those into moles. So 1.198 grams of carbon, multiplication sign and a line, 1 mole of carbon on top. Atomic mass of carbon is 12 grams, and we're going to get that value. So when we multiply 1.198 times 1 divided by 12, we get 0.0998 moles of carbon. Let's do the same thing for the hydrogen. 0.302 grams of hydrogen, multiplication sign and a line, 1 mole of hydrogen we know is equal to 1 gram of hydrogen. Our units are going to cancel, so 0.302 times 1 divided by 1 is 0.302 moles of hydrogen. The next step is to divide by the lowest number. So the lowest number out of carbon and hydrogen of calculated moles is obviously the carbon. So I'm going to divide each of these by 0.0998. So this is obviously going to be 1, and this is going to be 3. That means our empirical formula here would be C1H3, or more commonly known as CH3. And that shows the ratio of this particular hydrocarbon is 1 carbon for every 3 hydrogens. Let's look at another example. What is the empirical formula of a compound that contains 30.4 grams of nitrogen and 69 grams of oxygen by mass? Fine, in this case, we don't have a total sample. They just give us our masses of our elements. So step 1, convert to moles. 30.4 grams of nitrogen, 69.0 grams of oxygen. Multiplication in a line. 1 mole of nitrogen, 14 grams of nitrogen. We're going to have our units cancel, so grams cancel grams. So if we calculate 30.4 times 1 divided by 14, we get 2.17 moles of nitrogen. Let's do the same thing for oxygen. Multiplication sign in a line. 1 mole of oxygen, 16 grams of oxygen per mole. I know that I have this set up correctly. If grams of oxygen cancel grams of oxygen, and I am left with moles of oxygen. So 69 times 1 divided by 16 is 4.35 moles of oxygen. The next step is to say to yourself, okay, which one is the lowest number of moles? In this case, it's nitrogen. So I'm going to divide both of these values by the moles of nitrogen, 2.17. This will equal 1. This will equal 2. Therefore, when I write my empirical formula here, it would be N1O2, but we know that the 1 is assumed, so really it's NO2, which means in this particular compound, the ratio of nitrogens to oxygens is 1 to 2. Finally, let's look at a challenge example. This is for those of you that are like, well, I got this. This is really not a problem. Give me something really hard. Okay, so a compound contains 53 grams of aluminum and 47 grams of oxygen by mass. What is the empirical formula of this compound? Step 1, convert to moles. So 53.0 grams of aluminum, 47.0 grams of oxygen. Multiplication sign in a line. We know that the atomic mass of aluminum is 13. That is going to be 1 mole of aluminum, equals sign. So again, we know that this is set up correctly. Grams of aluminum cancel grams of aluminum. So 53 times 1 divided by 13 will be 1.96 moles of aluminum. Let's do the same thing for oxygen. Multiplication sign in a line. 16 grams of oxygen per 1 mole of oxygen. Make sure that our units cancel down and to the right. So grams of oxygen cancel grams of oxygen. If we take 47 times 1 divided by 16, our answer will be 2.94 moles of oxygen. Okay, next step is to say which is the smaller value. We notice that it is aluminum, so we're going to divide both of these by 1.96. 1.96, and this is going to equal 1, and this is going to equal 1.5. That's not a simple one to round up or down. We can't just say, well, I think I'll just round it to 2, because that's really not close to a whole number. So in this case, we need to take both of these values and multiply them by 2. So we do get a whole number, which means the aluminum is now going to be 2, and the oxygen is now going to have a subscript of 3. So the empirical formula in this case will be Al2O3. Now the question here is, does this make sense? And it turns out that it does, because if we uncrisscross these subscripts, we can see that aluminum would have a charge of +3 and oxygen would have a charge of -2, which it's like, yeah, that's sort of cool, because we know that this 3 is coming from here and that 2 is coming from there. Our metal is going to have a positive charge. Our nonmetal is going to have a negative charge. And in the end, this all works out. So in situations like this, it's sometimes common to say, does this make sense, and to check your work. So what did you learn? We went over the basics of what is an empirical formula. We talked about the difference between molecular and empirical formulas. We worked through how to determine an empirical formula, and then finally we did some worked examples. Need more help? Feel free to contact me. Have a great day.